I'm very pleased to introduce John Côté this morning.
Okay, thank you. Okay. Everybody sees the title. Okay. So everybody's here to know what the metric trick is to integrate in time in parallel. And it is so, actually it's so simple that I'm ashamed to present that here, but I'll do it anyway.
Probably don't have focus.
It doesn't like that. Okay, this works. Well, okay. So I skipped the table of contents, it's very simple. So time parallelism. So it dates back, the idea dates back to an old paper by Gelt, Communication to the ACM, something like that, in 1964. It's a very short paper, and it describes the principle of the method. And the worries that they were having in 1964, what if we have too much computing power? So his idea was, well, maybe there's the need to parallelize seemingly essentialist serial algorithms, such as solving evolution equations, to obtain a real-time solution on highly parallel computers, 1964. So the crucial point was, well, if you're worried about real time, then you do redundant operation, but you save in the real time. That's where. So one of the beneficiaries, of course, is numerical weather prediction. It was even stated in the paper. And he said, well, that more general and improved versions of these methods will be of great importance when computers are capable of executing many computations in parallel become available. So why time parallelism in NWP? So one thing is that, okay, so I don't need that. So the main argument is that parallelism is going up faster than the resolution in operational model. The point of view I'm taking is that you have all done your job, and there's 10 times more cores than there are that are available. So you want to use that 10 times fold more processors to reduce the real time of your forecast. That's the main idea. So in any situation, you fix the resolution eventually, and you equilibrate the physical parameterization, and then you say, well, with that model, with that horizontal grid, I can use efficiently so many processors. And the situation I'm describing is that if there is 10 times more processor than that, then you need to do something, otherwise this is wasted. Or if you can work the equation around and say, well, I'm going to use these to accelerate my equation and my solution, my time to solution. And okay, and also, you know how to parallelize using the main decomposition ideas in the horizontal, but in the vertical, one would like to have everything in core so that you don't parallelize in the vertical usually, except with some open NP loops and that kind of thing. So then the time direction should be parallelized. because that's the only workaround. So this is still a research problem, and it's not really for tomorrow morning. So let's make a thought experiment here. Suppose we have the solution of an ODE or PDE with a small time step delta t for a duration big T. Now if you were to sample at a large delta T once in a while, and then for each of these time slices, we were to start our integration from the solution we had sampled. This could be executed in parallel. The integration could be executed in parallel, and we would recover exactly the same solution as the serial solution that we had initially.
What are you calling a time slice? Explain again, what do you mean by time slice?
Well, I'm chopping my
Is that
my whole span into small time slices, and I'm taking a boundary condition for every of these time slices from the serial solution that I had doing pedestrian work starting from beginning to the end. So the second integration will give exactly the same thing, because if you have the correct boundary condition, then you get the same solution for each slice.
I see.
So
Zone is not that here it is highly the solution at the time step Tn plus 1 is dependent on Tn.
is what?
Dependent.
Dependencies. there,
No,
right?
because you have given the initial condition, the exact initial or the discretized initial condition at many points. So you are seeding, you are shooting, but for a short span, every.
But how do you know those values?
Well, you have to read the rest. So that the second solution is obtained much faster in Ward clock time, because you can do all these all these slices in parallel. Suppose you are divided in 10, then it could be done 10 at a time, and so the Ward clock time is divided by 10. Good. Elementary computer science, and Jan is agreeing. So the idea is exactly what Dave asked. Well, how do we know that we have the right initial condition? And of course, we don't know them ahead of time, as Nick said. So the idea is to start with the wrong guess. Yeah, the best guess that you could do was just to use these large slices. They define a time step, so that's a very coarse time step, and you integrate and you get a first guess. And the trick is iteratively to solve and correct. So you predict and correct. So it's a predictor-corrector scheme. And you inject into the coarse solve that is done sequentially, you inject certain information, you are nudging the solution so that eventually, as you iterate, the coarse solution at the initial that you use for the initial time step undefined with defined time step is converging to the one that you would have obtained serially.
Is it a multi-grading time?
Yes. Yeah, so it's many things actually. It can be looked at in different things, but it's one of the things is multi-grading time, or multiple shooting, or whatever. So It has
Multi-grid community called it waveform relaxation.
also they call it waveform relaxation for semiconductor simulation. So because it's related to electric wave. So that's the principle of the method. It's very simple. And actually I can, for people that are more visual, then, okay. Suppose you have a coarse gas, so you're doing a fine integration, F, and a coarse. Now since the algorithm was devised by French, so French mathematicians, so Madé, then coarse is G.
This is the tire.
Grossier. Yeah,
So
that's
it
the
calls
parallel.
Prof.
Or the same family, but this one is, it depends on the precise way you do the update. So your coarse integration is these lines, and schematically the fine integration are these curves. And of course the end is not coinciding. So you have to make an update here that eventually would reach that. And eventually you would get one continuous fine F curve. And for the method to work, it has to converge in 2 or 3 iterations.
Surely that. How many iterations has to converge? It's just part of the performance model. It depends on lots of numbers that you haven't yet specified.
Yes, well, that's why we
Yeah.
have half an hour. So here's the MATLAB code, but it's so simple. So that's for the parallel algorithm. So actually it's so simple that even that I put blank lines and comments and things. So this is real code, so I can execute that, and if I define that properly, so use the same name with a key to do a final coarse integration, because I have to prepare something in advance. That depends on the time step. I don't want to do it all the time. So
this is this code is a 2-level method.
this is a 2-level in time method. So I start with the first guess, a very coarse integration. So I'm doing large and big and time step. And then I start the loop. So I can do this in parallel. So since I have all these seed values, I can do one time step starting from that with the coarse integration, and m time step of the fine integration. So I get these vectors. So I'm taking just the n value and I'm storing. And this is done in parallel. And then this is the correction. So this is the predictor. And the corrector is then to redo the sequential integration, but feeding it a source term here eventually. So if you look at the way this should work, if it converges, this becomes equal to that. So that's the value at the next iteration. And so this goes to 0, and we are left that big U and F are the same at these common points. And that's really all we care about. So what are the conditions for fast convergence? Okay, you have the property. So if it converges in just a few iterations, then you're ahead for the real time. But of course, it's at the expense of increased CPU time. So every time you have to do one iteration. It's equivalent to the time spent in CPU doing a serial integration. So it multiplies that. And And there's no need to iterate to machine accuracy, because if you have some error in the discretization f, then it's just enough to iterate until that tolerance is reached. So you have some gain here. And efficiency, which is maybe a little less important, but I've assumed that the number of processors is the number of large time steps. So, okay. So analysis, there was a stability analysis. This algorithm was about 10, 12 years old. And so there were lots of work initially, for instance, stability analysis. And there's a very disturbing thing here. So it can be unstable if the imaginary part of this schematic equation is much larger than the imaginary part, like the diffusion. So it doesn't like pure oscillations or advection equations. Of course, that's...
Starts to sound an awful lot like the systems we're interested in, right?
Yes, I know. That's why I'm looking at it. And that's why, actually, this type of problem was not looked at in this context, in the context of NWP initially, because it's the hard part of the algorithm. But actually, there exists a workaround. If you make a projection to Krylov and so on, you can stabilize this thing. And actually, it works for nonlinear, but this works for linear systems for the moment.
Acronym. That's an unfortunate acronym.
Peter, no, but I think I'm not sure, but the guy behind that, I think, is from the Middle East. That's his bread and butter. So actually, he's working for the National Defense in the US, and he came up because he had this problem because he's studying the vibration of an aircraft jet, fighter plane, and so he's interested in having the solution quickly in real time to do the design and so on. And he found out there was, that's one of the concurrent algorithm to parallel. There's Peter and there's another one. So there's a whole family, but they are all about the same spirit. And he found out the first one that there was an instability, and he found a workaround. But because I've been working with Gandher, he was in Montreal at the time, and I was working with him. So I followed more or less his work because he has done a lot of work on that. But he wrote to me 2 weeks ago that, oh, maybe that doesn't work. So I've stopped working on that for the moment. But I've reproduced most of his previous work. So that's not, so when it converges very fast. And you see how it works is that the way the corrections are made, suppose you start with n blocks, initially the first block is correct because you have, this is God-given, the initial condition. But then after the first fine integration, you have produced with the fine integration the end condition of the second block. That will be the initial condition for the second block. So the way the correction is made, this correction goes exactly in it. So it's a direct method in disguise. So I'm sure if I iterate enough, if I iterate for the number of processors then that I have, and the time slice, then I'm sure to recover the serial solution. But of course, I've wasted my time and yours. So for sure the method will converge eventually, but it might diverge a little bit before, so that's the problem. So, but if it converges very well, and that's what I see here. And yeah, I show some stability analysis, so it's related to the meeting, implicit Runge Kutta. So there's a family that's called Rado, so there's Rado 3, Rado 5. For some reason, they are the favorite method for people working in ODE. And so I'm reproducing here the stability analysis of Ronquist. And actually, you can, if you have a problem, an ODE problem that you solve with this method, you only need, and the find and coarse method are solved with the same algorithm. So you just know the transfer function, and then you can plot, and you can have the amplification factor for each of the method with a short time step and with the long time step. And of course, with the long time step, it has to be stable. With the short time step, it could be conditionally stable as long as you satisfy the condition. So you can obtain an analytic expression for the amplification factor of each iteration, given these two amplification factors. And what happens is that you can plot the region of stability, and you see the problem here, that this red is the unstable region. So this is for, so it depends on the ratio of coarse to large, but anyway, you see that you have region of instability.
Sorry, John, so tell me again the difference between the left and right panels?
Oh, it's just a different exploration in parameter space. So on the ratio of course to find.
So on the left panel, then you're saying that I expect to have for a hyperbolic system, I should have my eigenvalues along the right, the imaginary axis. So once you get beyond that
So this is all diffusive, and this is the oscillatory. So there's a mirror image underneath, so I adjusted the top. But if it was unconditionally stable, it would be blue.
Sure, right. So, but what I'm saying is, if you look at the right side of your left panel, where you get from 0, you're blue, you're fine. Now you're on state. No, just keep going straight up. Go back to the 0. Yeah, right there. Just go straight up. Right. So there, now you're hitting an instability. But if you go beyond that, you're stable again.
Yes. And if you change the parameter, you see more islands. So,
What's the parameter we're looking at?
I don't know. As you get old, I did that a few months ago, so I don't remember exactly, but I can check. I did the other parameters in the paper. I'm sorry for not being more precise, but it's just.
Is it because when you get up there, you kind of, in some sense, you're so close, you no longer see the oscillations? The oscillations are kind of rapid with respect to the.
Well, the principle is this series, which is very simple.
So I think it's the ratio of lambda and lambda.
Yeah, it's the,
or the difference.
It's that thing
Change
makes
that.
this divergent or unstable in the sense that this becomes larger than 1. So it's just comparing the two amplification factors.
So is it some sort of resonance effect if your short time step and your large time step are certain difference, then you get these kind of.
Yeah, this is interpreted like that.
Yeah, I think that's kind of similar to what I was saying. I mean, basically, if your long time step is sufficiently coarse, then the other one is just vibrating; it doesn't see it. The problem is if the scale separation isn't enough, then they're fine, and then you go blue.
Okay, but in numerical weather prediction, we are saved a little bit. Because things don't look as bad as this analysis says, because the diffusion occurs, the problem occurs in a small scale, and the if dispersion is normal, and and the diffusion increases with the small scale, usually. So it will not be as bad as that. But, of course, this is a warning.
Before you leave that, this is looking at stability, but thinking about what David just said, going up that axis, the imaginary part of mu delta t is getting huge. And so that means that, yeah, you're jumping many periods of the oscillation
Right, and
in one of those big steps. So I
once you're no longer
don't
in
see
the
how there's
linear
any information there anymore.
Right, and once you know the linear regime, what that actually means is that you have so many more opportunities to have jumped onto another realization, basically.
Right.
At which point it's really obvious that you get anything out of this.
Well, the workaround is, with the projection method, is when you replace the ODE problem with the linear algebra, is to do a lot of linear algebra to make sure that it stays on the correct trajectory.
So just taking a very simple example, if you were solving a simple single wave oscillation problem, how far out in time would you take these course steps relative to the period of that oscillation?
I can show some examples later on. So there were lots of applications. So I've done, oops.
I'm really scared by the first one.
Finance, yeah, I know. but
Your money's in that month.
actually, it works very well in finance. Means that you
because
can
they don't
lose
really
money
care
very
about
quickly.
My money's so safe that the government had to nationalize my bank.
So molecular,
Think
so a lot
of
of things work, and even Paul Fisher here, that was here, but is not always here, I solved the Navier-Stokes equation with that algorithm with diffusion-dominated flows. So if you have more or less or trickle, it works. Reservoir similar. So there are lots of problems where it was used, but I looked at, of course, the problem is with the advective part and the wave part. So, and I've redone most of the things that are in blue, so I know more or less the problem. Oops, why doesn't that work?
You need to click on the thing again because you don't have focus.
Okay. So there's the redeeming feature is that there's a wave number dependence. Well, so since we have analytic expression, I can try to play and see if I can come up with something for the semi-Lagrangian advection, for instance. So the real key point is that the two lambdas have to be close enough. And my initial question was that if you keep the advantage of this long time step that the semi-Lagrangian scheme gives you.
So you haven't tried these older waveform relaxation, the multi-level ones yet, or is it not really worthwhile going to multiple levels?
It's not worthwhile, I think. Well, I may need some further investigation, but even that doesn't give you too much. But I think. So results so far, well, I've done some work towards that here, so it's not completely true. But it works for well-resolved waves, so that's a good thing. So for semi-Lagrangian advection with cubic spline, you can do the analysis and you can find the absolute value of lambda, and it's very good. It's almost one everywhere, then in the end there's some damping, but actually the problem is that there's too much damping here. So the problem is not uniform in some way. It depends on the residual current number. So you can be with very high current number, and it will work. So if I want to cook up an example, I'll give you I mean, the scheme is virtually exact for integer current number. But the point is that there will be a problem because you would have this part close to 0 and this part close to 1. So for numerical weather prediction, my friend Gander has looked at the Lorentz equation. So since he's not a meteorologist, that for him that's very much the numerical weather prediction. And there was an effort at DWD, the German Weather Service, with starting the results were presented last June, and they were looking at 1D problem. So the conclusion of that paper was that it worked, it cost to do the linear algebra to work around, and but they used also, there was some damping, which I don't like.
What was the main result of Gander and Hera? Because that's the one I'm really interested in at the moment, is when you hit it with a chaotic system, which is the Lorentz equation.
Well, actually, it was working. I suppressed the result here, but I can show you afterwards. Or, I mean, if we have time. We're already out of time. So my project is stability and convergence, performance gain. So it's interesting to have measured performance model that works. Choice of scheme. So the fine grid scheme could be explicit and or split IMEX type, and the other one needs to be absolutely converging. So we have to look at the stabilization mechanism and the ratio between the fine and coarse grain time step to see if it's worth spending more effort. And there's something interesting is that because it's a multi-grid method, what you can do, and there's an example that I did with that seemed to work, is that you can, the coarse time step model, you can reduce the time, the spatial resolution, therefore you can have more or less the same CFL number on both the fine and the coarse grid.
I'm just still coming back to the question with the multi-level, because you've said to us that you cannot choose the difference between fine and coarse too large. That means you basically have limited to yourself to a parallelization gain of 10. Because
well, there are some cases where I mean, if I were to model, what do you call it?
But I mean, this is
so it depends over permanent the soil moisture, the soil that's frozen. I can use a time step of 1 year.
For special cases, but I'm just saying that's the permanent question with multi-level versus two-level. Is if you don't go to multi-level, you're just blocked. I mean, you've got that gain of that one short, a longer time step. That's it. That's a fixed maximum speed up you can get.
Yeah, but practically we can't. I mean, it's very unlikely that we get more than 10 times the amount of processor that we need for one forecast.
Are you kidding?
No, I mean, suppose that we have done the parallel things. Suppose we have been successful.
Yeah, but
and we can use.
But if your algorithm works, it's perfect for like GPU or something like that.
Yes,
it's
with
completely
GPU.
parallel.
Yeah.
So if you
no, it's not completely. Each model is something that has to be mapped somewhere. So it's not completely parallel. So for ODEs with or schematic problems, but not for a complete full model with physics. It needs a computer, and so it's like having 10 computers and working in parallel. And of course, I always challenge people doing iterative schemes to give me something better than my direct solver. So eventually, they will succeed.
Forecasting instead. ensemble forecasting, so you just run 10 or 20, 30.
Yes, but you're limited in resolution, and
But you're saying you've got enough resolution as you want. You have a fixed number of grid points. But
No.
you got more processors.
no, but if you
no.
what you want is to reduce the workload time so that the forecast that you do is delivered quicker. It's important in North America because the East Coast and the West Coast are very far apart. And also this thing has not been looked at. What if there is some delicate balance? What if you jump time step? How is it maintained? So here's my roadmap. And so I've reproduced that. And Berger's equation, I have the analytic solution, therefore I can
That's a pretty diffusive Berger's equation when you're running that around.
yeah, but that's because I was using the same parameter as Gamba. But I've done other experiments, actually, which were less diffusing. So not all the details were given in the paper, so I had to cook up some method. But is the initial guess, that's a final solution, but and the red and the blue are very close to each other even after the first iteration. So that's one case that there's the norm going down, and there's the error compared to the analytic solution. I tried to come up with a setup that was more relevant, with less diffusive, and with a CFL number of close to 1. And I did a lot of time step. I think it goes around a few times, but the damping is not so large. And what's interesting here, well, you can compute the exact solution. And I wanted an interesting mix of waves. So this is the delta function with 10 waves on that grid. And that's interesting. You see the red and the coarse resolution in blue, the same color code, and it converges. But what's interesting if you compare to the initial solution, and that's important, the algorithm should converge to your final solution. And in that case, because it's semi-Lagrangian and all that, so the behavior is sometimes strange. You can come up with a large time step that's exact, for instance, or more exact than with a fine time step.
What was the large time step in this case? Less than the oscillations or more?
It was a factor 20. Yeah, it was.
So there's less than 20 humps, okay.
So the large time step is closer to the exact solution actually, but we see that it converges to the fine solution in blue. And here's the convergence history, and as mentioned before, it's a direct method in disguise, so it will come up to 0. And MATLAB is intelligent enough not to draw infinite. So you can repeat with the same parameter with the semi-Lagrangian algorithm, and then it's very good even at the initial time with a large or small time step. So there's a factor of 10, and so what I've done is I've almost finished the advection diffusion equation, and I've done also the things with reducing as well as spatial resolution of the, but it's not so, I've not done all the cases. And I've started the case of either pure advection or just oscillatory problem, just to see how this would work. But actually you replace without even, you just do the coarse iteration, you do the projection Krylov part, and actually you're already on the exact solution. So it converges in one iteration. So
That just tells you your problem's too easy, right?
in a sense, yes. So I suspect that some of the test cases that were done with PDEs, especially, were more or less cooked up example. But with ODE, it seems to work if you choose the right type of ODE. So in the future, I want to look at pure advection again, because that's the key problem. Modified Peter. So I've looked at parallel, but I should look at some other implementation, because modified Peter seems to work with nonlinear problem, but the other parallel is limited to, for the moment, to linear problem. So eventually, so if I go above this hurdle, I can look at the shallow water in 1D, and then beyond that, the sky is the limit. So 1, 2, 3, infinity. Thank you.
So has this successfully been used to simulate high Reynolds number turbulence? Because this is the issue, right, is that we have small changes in initial conditions. We believe we have a chaotic system, and we're going to have very different ultimate outcomes from small changes. And when you try to make an adjustment to match these trajectories, basically you're never going to be perfect. So you're going to have some small imperfections, and if your system's sufficiently chaotic, it seems like there's no way you're really going to be able to get back to the single long
Okay,
time.
I think I should show up the this is a very sensitive equation, because when you see the scale was chosen automatically, it's a three-body problem, astronomical, but after the first iteration, the scale has changed and it converges exactly. So this thing has to be in the initial.
The coarse scale.
Hmm?
The circle's the coarse scale or the fine scale?
No, this is the coarse initial solution, and it's really
so
bad.
So your coarse scale has to be quite short with respect to your Lyapunov exponent, right? That's the.
Yeah. I was going to say your advection, 1D advection problem is an example where you could test very quickly these questions that people said. If you just change, rather than changing lambdas, if you change the frequency of your oscillations and see how robust your algorithm is with respect to that. Because I would guess it breaks down once the frequency gets faster.
Yeah, well,
And if I understood you right, you were saying you cannot predict what frequency you're going to get.
so is the
Well,
one-
that's the key point, is that these things are all changing. It seems to me a linear problem, you can make an adjustment once you know how far off you are. A linear problem, you should be able to push it
No,
right back to
the,
where it was.
the algorithm is supposed to work with nonlinear. Right? It's just that the problem is with parallel is there's a problem with the turbulence or the diffusion part, but it doesn't mean that it doesn't work with nonlinear problem.
It's gonna have
For
a
instance, this is the starting point of the Lorentz, so I start the Lorentz. So I use a ratio of 1 to 80. So I choose the time step, the ratio of time step is large. So initially you see the continuous curve and the dashed curves are
But
separated.
it's not the ratio of time steps that's really the problem. It's the ratio of what the coarse timescale is allowed to be compared with the timescale in the actual problem. And so that, and in order for that to be a kind of useful thing to do, that's got to be quite big, and that's not really obvious from here.
Also, the most metrological codes will run already quite close to the limit what they're allowed with long time steps. So you're often gonna find it hard to make it even longer time
No,
step,
but you
stay
use,
stable.
but the coarse method, you use a long time step, but you can reduce the grid size as well, and you can use more implicit method.
But
So
you don't
you're not
have any
limited.
expectation of staying on the same realization of your Curly orbit by doing that.
So you mean that like run a coarse resolution problem, get the solution, use that to initialize the high resolution.
Yeah, because the way it works is that from your fine resolution system, you feed, you modify, you add a source term. Actually, the guy who proposed the parallel algorithm was Jacques Louis Lyon, and he died unfortunately soon afterwards. But I mean, it's related to data assimilation problems where you have the wrong curve for variational 4D assimilation. So yeah, the problem is you want to find the initial condition that will best fit the data and your past forecast, so a mix of the two, for a certain length of time. And from the misfit, you compute with the adjoint, go back and correct your initial condition. So it's exactly this type of algorithm that's given here. So that, except that it turns out to be very, very simple in this implementation. But there are some ideas behind of the adjoint. So even if the flow is turbulent, it means that there would be no data assimilation either.
But I think David's comment is the right one. Is there some physical time beyond which everything is completely decorrelated, and they vary as a function of scale. So if you are trying to run a fine resolution model, you have active convection, all kinds of stuff going up, you can't paste that all back together and get it to work right by doing something.
No, but you are adding a source term in the course integration. And this source term is enough to compensate. Because the course integration is on a slow manifold.
You're solving a optimization problem where you're trying to, in some sense, descend the basin of attraction of the orbit of the discrete system which the fine scale is following. And that's only really likely to work if you're actually in that basin of attraction, so you have to be really quite close. And that's one of the reasons why even optimization based on having the right gradient in some sense with an adjoint is often really quite hard. Because you don't know where you are in relation to that, and when you start with a chaotic system and you start taking big steps, that you really have problems about whether or not you expect to be in a basin of attraction that actually gets you back to the fine scale orbit.
As what's his name said, Galileo, but it works. Sometimes. So if you see the different component of the Lorentz equation after so many iterations, you see that the beginning of the orbit, the beginning of the orbit is beginning to be, so even the coarse integration is converging to the fine integration.
But the coarse integration is still resolving that orbit brief. Oh, right. That's the...
No, that's an interesting. I've invented the Eulerian finite number. That's it. Oh, and from all the questions, I realized that I don't have all the answers. And there's the pudding is in the eating.
I think there is a related idea which I think is really exciting. So as you probably picked up, pretty skeptical about this one. But there is a related idea which I really do like the sound of, and that is, so one of the things we do, especially with big climate runs, is people then in the years, say in the years after one of the intercomparison projects, scientists all over the world spend enormous amounts of time studying those outputs. And one of the things they do is that they compute diagnostics that were not in the original equations, not in the original simulations. So as we massively increase our computers and therefore massively increase both our spatial and temporal resolution, this causes a real problem because we can produce more and more data, we can't store more and more data, we can't move more and more data from storage onto a machine where we can actually compute the diagnostics, right? We know that both network and storage are scaling much, much more slowly than our ability to compute. So how are scientists working with the fifth inter comparison, the sixth inter comparison, going to get the benefit of the additional spatial and temporal resolution? Well, one answer might be, we don't store everything. And this is where this comes in. Because one of the things you could do is you run your climate realization up against whatever your strong limit is, which is a small proportion of your machine. And you run it, and it takes you however many months it takes to do the realizations. And what you do is you checkpoint every so often. And then you don't have a full set of realizations on disk. What you have is a set of checkpoints. And now what your climate scientist does is says, okay, I want to study this. I somehow, preferably with a nice language that enables you to do it, provide you, the climate center, with the query that I would like run that will produce the reduced diagnostic data set that I'm interested in. Now what happens is you periodically or on demand, depending on what the economics of the situation are, you rerun all of these checkpoints. But now you can use your trick, because now you don't need to run the whole thing from start to finish, because you've got the exact points to start from, and then you can run all those in parallel. And then you can use all of your machine to rerun that sort of information. And that enables you to substitute compute, which you've got, for storage and network, which you don't have.
It's not quite the same thing, because now you've just, all you're saying is you do checkpointing and you recompute. I mean, this is actually starting with the wrong checkpoint and then you iterate.
No, I understand that there's difference in that sense, but that's why this works and that may not. And even then, actually, it's still challenging. It still depends on, it strongly depends on bitwise reproducibility, because if you don't bitwise reproduce your checkpoints, which is an expensive thing to do, then what's likely to happen is when you rerun these, you end up on different realizations, and then you have a jump in your system. And then it's not at all obvious that even for the sorts of things you should believe from a climate model, sort of statistical properties that should be invariant, it's not obvious that those are still invariant when you have jumps in realization all the way through your system. So it's still challenging.
Why are those jumps a problem in the climate context? It seems like, so you wind up in a somewhat different state in 2080. At the checkpoint, you've got 5 years or something of.
Maybe it does make
at least like climate scientists, I can't believe that they're really asking us to do this. I mean, they are constantly saying to us, we need to have pit reproducibility. I say, like, it's rubbish.
No.
You've got so many errors in your code.
No,
why do you want to have pit reproduce?
So I'm not claiming that you need it. So I'm merely concerned that if you have a set of, whether or not having a set of checkpoints which do not themselves constitute one realization, whether that is equivalent to having, statistically equivalent to having ones that do. That's not at all obvious to me. And it certainly would require very careful thinking about what sort of diagnostics you're allowed to compute when you get near one of these jumps.
Yeah, you don't compute them across the jump. That would be the whole idea.
Well, but that's not completely obvious, right? If you have rolling averages then, and we have rolling averages which then cut out at particular points, what did that just do to your statistics? And like it's a little bit.
You might get sort of like suddenly El Nino will terminate very.
Right.
El Nino will
Exactly.
terminate very rapidly.
So if you start asking questions like how long does El Nino typically last, and then you've got an El Nino where there was a jump halfway between and it instantaneously switches from El Nino to La Nina, what does that do to your statistics?
Oh, just that these days people are studying the
There is-
extremes
at
of
that
it, so
level
you
too.
need the daily data to look at the sequences of very hot, very dry days and all that sort of thing. And so you do want it reproducible to make it consistent with what you got from your average climate.
But I think
But I mean, there's always bias from the numerics in there. And so I'm always saying, why do you care about the bits if you have already bias in the system?
If your science depends on the bitwise reproducibility,
Consistent,
I agree you've asked the wrong question.
no science should depend on that.
Right.
The statistical equivalence.
I completely agree.
That's something
What
else.
I'm not clear about is whether the statistical equivalence is maintained if you have jumps between realizations in your realization. That's what.
David, at that scale, what matters is the averages, right? Not the instantaneous.
Well, but the problem is, do you get this? So I agree. You should. only be looking at statistical quantities. The question that's not obvious to me at all, I think Chloe just came up with an excellent example, is it's not obvious to me that you get the same statistics out of a set of short realizations with jumps that you get out of one longer realization. So the bare minimum, you would have to be very, very careful about the way you formulated your statistics if you were going to run that system.
Statistics that average over a number of time steps as well as spatial statistics.
Your particular application was to try to get your NWT forecasts out faster for a given resolution. Right? I'm just curious, what is the resolution that you feel is good enough so that you wouldn't want to invest more computer power if you had it on further increasing resolution versus just running faster?
It's a political question, I think.
Well, it's
because it depends. We knew a long time ago that we should do global forecasts, but we were prevented from doing it because politicians, we are not in the business of doing global forecasts. So that's simple. So,
well, but for your NWT forecasts.
but even for NWP, it was we had a very increase in performance after going global, just because we did so long, but when we got global, a lot of our disappears. But I think people are thinking globally 10 kilometers probably enough for, because if you look at the
So you don't think we're trying to starting to explicitly represent convection in the non-hydrostatic regime will be beneficial when we get this?
Well, global,
advanced?
it depends. Globally, I think people think, well, 10 kilometers is probably enough.
Enough, certainly
But local,
for hydrostatic models.
For local scale, regional scale, or continental, depends on the customer need, but people are thinking in terms of kilometers, or even sub-kilometers for cities.
So right, so I see Joe's question is, why not just